All right, so we're ready to go. So today is February 19th. This is week 6. And let me start with a couple of announcements. So starting with project 2B, we're going to be doing these projects as pair projects. So I think there are probably about 3 groups that haven't been formed yet. So please, form these groups as soon as you can, and let me know about the groups. Okay. The process is just try to finalize this today, maybe during the day, during the break, and then for each group that has been formed, just send me one quick message with the group members, and then I will create an entry for you in Sakai under the item team. So there should be a team number. If you don't have a team number, it means that I don't have a record of you being part of a group. And if you think you've already formed a group and you don't see a team number, let me know as well. All right? Any questions about this process? Okay. Very good. So it's really important to do this soon because you will want to be able to make very quick progress on these projects. So 2B is essentially the same as 2A, but making it, redoing 2A following the algebraic expressions example. So that's the part that we're going to go through today in the second half. All right. So I think the approach, kind of the background material is a bit challenging. So it'll actually help to have someone to bounce ideas back and forth with. So that's the idea. So please wrap this up today. Then the project repository structure, let's not worry about it for the past projects, so I think it's okay for me to have noticed now. I messed this up completely, and I apologize for the confusion. The way we need to do the project structure is very simply, and we'll do it like that going forward, right? So going forward, there'll be one repository per team. So per these instructions here, it's not on the instructions yet, but the project name should be, the repository name should be CS, let's see, it could be, right, so it could be under either project member, or under either group member's name, right, and then it should be CS372 S14 and then team and then the team number. I'll add it to the to these instructions actually. So let me add it right here to 0B. Okay, create your shared team repository under any team member's Bitbucket account, and call, we'll call CS372 Spring 14 Team N. Okay, where N is your team number from Sakai. All right, and then share this repository with the instructor as you had done for your individual repository. Does that make sense? Any questions? I think this is how we did it. So now the structure. So that's the part I was going to clarify. So I changed it here but don't go back, obviously, and it's already graded for everybody whose submissions I have received. So if you haven't submitted the work for Project 2A yet, you really have to do this quickly. I don't want anybody falling behind on this, because we have to kind of build gradually on earlier work, on kind of more foundational earlier work. That's how we make progress. Not only forward but also upward progress. Right? We want to take things to another level intellectually. That's why we're all here. So anyway, the structure is like this. So the silly thing that I had forgotten to mention, or I had not thought, so you have your repository. So going forward, it'll be this shared repository. So let's say CS372 S14 Team 1, okay? And then within that, you will have a Project 2B folder, and you will have a build.sbt in the Project 2B folder. So you'll basically have, for each Scala SBT project, you will have a subfolder in your repo, and that's fine. It doesn't have to be one Scala project for the entire repo. Does that make sense? So that would have made things easier. But that way I can run, for example, that way you have a separate source structure for, let's say, Project 2B, then later for Project 3, etc. Okay? So with a separate build.sbt file. And I think it says this in here as well. Yeah, so here. Keep this entire project in the folder Project 2B within the structure of your team repository. So meaning that Project 2B is a self-contained SBT project, and Project 3 will also be a self-contained SBT project. And they just happen to be within the same Bitbucket repository, within the same Mercurial repository. So that's fine. That's a common way to structure, let's say, related projects, so that they're just under one repository. So it's a mapping from one Mercurial repository to 0 or more SBT-based projects. And there could be even a coexistence of SBT-based projects, Gradle-based projects, etc. So I think this is the right structure. It's going to make it much easier. As I said, those of you who've already received a grade, don't waste time going back. Otherwise, if you haven't submitted yet, maybe do this. It'll make things easier for you and for me. But try to get this done. Try to get it out of the way. It's really not hard. And you've already done basically the same thing in 313, 413. So there shouldn't really be anything holding you back other than getting up to speed a little bit more with Scala. And I'll be happy to help if you have any barriers or so that you need help with. Okay. So Project 2B is here. We'll get you to where this makes sense. The deadline is March 1st. That's a Saturday, right? Yeah. So that should be the Saturday before spring break. And it'll give you time to look at it in detail, and we should be able to eliminate any remaining obstacles next week. So that's the plan. And really, if you look at the expressions example, which we will do in detail, it's basically just like that. There isn't that much to do, and then you just do a little bit of these reflections, and then you will see it'll all make sense. Okay. Very good. Any organizational questions at this point? Are we clear on everything? Okay, great. So there's one thing I wanted to share with you. This is a kind of technique, a very general technique that's going to be useful as you work with Scala. It just came up this afternoon as I was looking at some stuff with George. So here's the example. Okay, so the use case is you want to convert a string to a number, And in Scala, there's, of course, this highly convenient, well, that's another example. In Scala, there's this very highly convenient toInt method. Let's look at this. So I can say 1, 2, 3, toInt. Oh, great. Works, no problem. Okay. So what about like this? Oh, didn't work. All right. Why? Well, there's that space. Okay, fine. So then a good way to deal with that is you just put a trim, and then it works again. Okay, fine. But then if it's input from the user, you know, let's say the user enters some nonsense like this, you still have this number format exception. So how do you deal with this when I've taught you for almost half a semester that you shouldn't be dealing with null pointers or exceptions or things like that, that there's a much better way to deal with this, which is what? Option, exactly. So how do we kind of bridge this little gap here? And there's a great way to do this, and that's why I wanted to share it with you really briefly. So there is a class, or actually an object called Scala util control exception. And this gives you a very nice way to deal with these kinds of situations. So we can import this guy, okay, and now we can use this factory method. So the import, we're importing everything from this exception object, and the catching method is one of those members, okay. So if we say like this, whoops, okay, so let's say we take this, and we put this, okay, let's see again, okay, now you see when you suspend it and then you get back into it, it somehow loses the read line part, you know, the editable command line. Okay, so let's put this in here, and now we need the import, but we can just, I'll show you, we don't even need the import technically, right? We can just use the full name of this method, and then, so the catching method builds a so-called catcher object up to where the cursor is, and that object has an opt method, and that kind of wraps around whatever comes next. You know, you can, if it's a more complex thing, you could use curly braces or so to make it look a little like a block. But so basically what's going to happen here is the thing on the right is going to raise the exception, the number format exception. And this opt method from the catcher will do the conversion. So check this out. So this is a lot better and also much easier to deal with, right, than a stack trace, because there are a couple of things you can do, right, with these options. One is obviously we can do pattern matching. So we could say match, let's say you read the string from the input, so you can say match the result of that whole thing at the top, and if it's some I, then we got our int value, right? Or if it's none, then we can say, oh, try again, or do whatever we have to do to correct the incorrect entry, okay? So we could use it in a match case statement, or we could, what else can we do with an option that's actually pretty cool without doing any explicit branching? So is there a way to say, well, let's use what the option gives us if it's good, otherwise, you know, let's give it some default value. So yeah, you've probably not played with it enough yet, but there's a method called get or else. So we can use for example, we can provide the default value. Let's see if this works syntactically. It might need a parenthesis around this. See? So now, because the option value was a none, it said, oh, I better use the default value. But if I have a good value here, there's no need to revert or fall back to the default value. See? So with a get or else, you just have a fluid way of interacting with the option. So it stays kind of a one-liner. So you say, okay, let's build a catcher. Let's run the number conversion within this kind of catcher environment. And that gives us the option. And then with a get or else and then providing the default value, you're still keeping it fluid, meaning the way you're invoking this chain of methods. And that's all you have to do. This is good when it makes sense to have a fallback value. Let's say when there is a meaningful default number of whatever number you're trying to read, okay? If there isn't a meaningful default value for the value you're trying to read, then it's better to ask the user to try again, okay? Okay, and then the other things you can do, of course, instead of the get or else, you can map the option, right? So you could say, you can say map, and then times 2. You can basically continue computing the thing on the thing that's inside the option, like this. See, so if this had failed, it simply wouldn't do the map, right? Because it would know that it's already a none coming out of the format conversion, and then it would know, because it's a none, when you apply a map to that, there's really no value to apply the function to, so it stays a none, except it goes from a none int to a none. Well, here in this case, it stays a none int, but it could go from a none of one type to a none of another type, right? All right, so this is just one more of these nice little things you can do with options to keep your code smaller, ultimately more readable once you're used to this style. And then you might also ask, well, where are the dots here? Well, it's the same style that you've seen in other examples where it's object, method, argument, method, argument, chain. So it starts with the original receiver, which is this catcher that we're building. Okay. Then we're invoking the op method, so there could be a dot here, and then we would need parentheses here. Okay. And then there's the map. So it could be a chain with dots. So the dots are optional, and the parentheses, whenever it's this alternation between methods that take one argument and the argument, right? So you start with the receiver, then you might have a method that takes one argument, method that takes one argument, argument. So you can have, an arbitrary length chain of that. Of course, you don't want to overdo it. You don't want to have long lines, so there's a trade-off. So at some point, if your line gets too long, then you could try to break up the line, or in some cases, it's useful to introduce names for intermediate values along this chain of computations. Great, so I just wanted to share this technique with you because I think this is generally useful. Any questions or comments? Yes?
So get or else, if I wanted to make my own object, do I have to implement something to get or else?
Your own object
like
that you're using how?
Object. Like if I want, so like if you have an object that has an option, some method with an option, like that would have there, and Can you just use get or else?
Yes,
on
yes.
an object?
So get or else, the receiver for the get or else is the option value. So the wrap value. So you're getting that always.
So the option has the get method as well, right?
Right, but the get again might fail, right? The get, when you use get, you're back in exception territory, possibly, right? Exactly. So, right, that would get you back to the starting point, essentially. So, usually the way you work with options is you either do this kind of branching using a match case, or you just, like here with a map, you kind of keep the computations, the things you do with the value wrapped in the option, you keep it wrapped, but you can continue doing this. Just as a preview in terms of terminology, this is the monadic style of doing with it. And you could do the same thing with a syntactic construct that we've seen, which is the for comprehensions, which is just nicer syntax for these long chains of computations within the wrapping. Okay, so I could do it like this. I could say for, and then I could say v equals, and then I should be able to put this. Okay, so it's just another example of this equivalence. Of course, you don't want to, if you use this frequently, you might want to create just one catcher and give it a shorter name. I'm just, for the purpose of the example, pasting this here. I should have used that arrow. Okay, let's do the arrow, right? So here we go. We have to use the arrow in conjunction with these four comprehensions. So now we can say W arrow, and the arrow means basically that we're doing a computation on something that's still wrapped in, let's say, an option or something else that has similar structure like a list, which we've seen. We've seen these comprehensions based on lists. So now we could say, for example, W becomes 2 times V, and then we should be able to say yield W. Let's see what happens here. Okay. Maybe let's try this again. I think we need first we need a sum here. I think we need a sum here to keep it wrapped. And then here, let's try this. Yeah, so this works. So the yield plays that role of the get or else. So let's run the thing again with a number that'll work, like this. Okay, and now the yield. Okay, so it works and it retains the wrapping. So then at the end, I might still want a get or else, only if I really need to get it out of the wrapping. So for example, there might be stuff I do within the for comprehension where at the end I don't, I've already done everything. For example, I might have printed something or whatever, and at the end I don't really need a value, then I don't really need the yield in that case. All right. Any other questions? Excellent. So, quick check. Is this? Yeah, looks like it's going. So this goes away. All right. So now we're going to be in kind of, we're going to take something that you're intimately familiar with to the next level. And this is really only for setting the stage for doing the real thing. So we're going to look at functions, at recursive functions, ordinary functions or methods. And we're going to look for the deeper meaning behind the recursion only as a warm-up so that we can then do the real thing, which is look for the deeper meaning behind recursive types. Okay, so let's try this. And we got the example here, which, the link goes here. Let me make this bigger. Make the code bigger. And I think, okay. All right, so here, let's look at the top. So I tried to add as much text as possible, just so that when you look at it again, you can reconstruct what's going on. So here's a factorial, and I deliberately wrote it as a function as opposed to a method. Method, it would look like def fac and then n int, and then there would be the recursive definition, so it would be the body would be the same as here. So here we're writing it as a function value and giving that a name. So here, this is your argument, and you don't need to say n int here because it already knows from this type annotation that the argument type of the type of the argument n is int. So it can, from there, it can infer the argument type and the result type. It'll know the result type of fac to figure out what the type is here when it applies it, when it's recursive. It'll tell you, in general, it'll infer as much as it can, but it'll tell you when it needs some additional type annotations. You just look at the error messages. So this is familiar. I could have written it like this, right? And again, if I didn't put the result type, it would complain because of the recursive nature of the method. All right, so I just rewrote it to tie it more to the examples further down. Okay, anyway, so if you look at just the function value, what it does is takes the argument n. If n is 0 or less, return 1, else return n times the factorial of n minus 1, right? So that's the same recursive function definition of the factorial that you must have seen maybe 150 times. Okay. Any questions about this? So it just calls itself recursively the usual way. You do this kind of stuff all the time, right? So you plug in a 5. So then it substitutes. That's also a good refresher in preparation for project 3. So just bear with me for a second. We'll understand exactly how the function evaluation takes place. So when we say factorial of 5, we say, well, what's factorial? Oh, here it is. Okay, what is it? Well, it's this value. Mapping argument n to the function body. And function invocation and method invocation works like this. We substitute the actual argument values for the formal arguments that are there as placeholders. So n is this placeholder. We'll substitute 5 for the n, and then evaluate the body, what's to the right of the arrow, the double arrow. Okay. So is n less than or equal to 0? No. So we go into else, and then we say, okay, the result is of this invocation 5 times factorial of 4. Okay, so that's the recursive invocation. So we'll have to call factorial again. And we do it now with n equals 4. So we go through the same thing. And ultimately, we have a chain 5 times 4 times 3 times 2 times 1. And then the 1 gives us 1 times factorial of n minus 1, which is 0. And that says, oh, now we need to do it for n equals 0. Okay, n equals 0. Is n less than or equal to 0? Yes. So we go into the base case. We just say, okay, now we can just return the 1. So that plugs it in, and then the whole thing kind of comes back up and performs these pending computations on the way back up and comes up with the final result. Does that make sense? So that's how recursive functions work. And then, yes, this is 120, of course. Okay. So the question is now, so there are dozens of recursive functions. What do they have in common? Well, the fact that they're recursive. So how can we kind of abstract out the idea that they're recursive and express them in some kind of non-recursive way? Okay. So here the idea is, let's look at this one here. Okay. So this is this prefactorial is a function that is very similar to the factorial, except that it's not recursive. So if we look at, in fact, we should probably write it like this. It'll be, okay, I think then I had some problems. Let's not touch it. Yeah. I don't want to bring any of these problems back. Anyway, so, but it's kind of like the recursive factorial up here, in the sense that, well, okay, there's this weird g argument. But once you apply the g, then it takes an n and has the same body as the one up above, except that instead of a recursive invocation, it invokes g. Okay. So, all right. So what's happening here? Basically, this is like the factorial above, but with with what was originally the recursive invocation of the thing itself, just turned into a separate parameter. So what is the type of the function that we're invoking recursively here? Well, it is the function itself. So that this is its type, right? Function from int to int. Okay. That's why we've chosen that type for g. So then instead of fac, we can invoke g, and the types still match. So it takes n-1 as an argument, and it returns a result that's also of type int. Okay. So it's okay to do this, right? And let's take a look now. Maybe let's play with this here in the console. Let me go there. So, okay, it defines these things. Now we can play around with them. So the factorial, if we put 5, it says 120. Okay. So the prefac, if we cannot just call it on a number. We need a g. Okay. So if we put the recursive factorial that we defined as the g, it should work, right? So after the first call, it'll then basically transition control over to the recursive factorial. So this should be the same. Yeah. Okay. But how do we get rid of the kind of implicit recursion? So what I'm trying to go is to say something like, can we pull out recursion as an abstraction, as a separate concern from the behavior that, the computation that will then be driven by the recursion? Okay. So, first of all, what I could do, if I have the prefac, and if I say, well, we can get back the recursive factorial by saying, well, let's just do the recursion on this first argument. So let's put, let's make g. See, so g is the first argument that the prefac takes. Let's make that the recursive function we're defining. Okay. So this is the part where it gets kind of hard to understand what's going on, but we will get there shortly. But basically, what you get here is equivalent to what you get there, because if you take this, in this invocation of prefac on fact2, let's just, again, how do you invoke the method or function? By replacing the formal argument with the actual argument in the body. So let's take the body, let's take this, with the n that it hasn't received yet. So it's n mapped to the body. And we're replacing, what does fact2 replace in the body?
The first argument.
Which is?
Which is a function, right?
Right. Which is a g, right? Exactly. So in other words, we'll plug in the fact2 instead of g. So what we get there is n of type int mapped to this if statement with fact2 being in there instead of g. So let's write this down. And let's see. I'm going to try one thing quickly here. Let's do this conservatively so I can bring it back easily. But I wanted to match really, so I was hoping that I was going to be able to write this, so that it would match literally what we have above, like this. Okay? Does that make sense? So now, whatever prefac produces, if we give it g, looks exactly like what fac already is, with the only difference that here we have the fac and here we have the g. Okay, so let's confirm that this works, because there's some subtle issues that have to do with so that's the thing. There's some subtlety with the definition here, and maybe we have to make this lazy. See, that's the thing. So this is something that I still need to figure out exactly what's going on. So let's leave this as a comment. So that's the intent, to make it look just like fac, but with the fac abstracted out as g, as an argument that is not hard-coded to point to the thing we're defining. Okay? So when we apply prefac to fact2, we get the fact2 here instead of the g, right? And now it looks just like factorial, right? So in other words, what I'd like to refer to recursion is as tying this recursive knot, taking something that you're defining and then plugging that into the definition itself, right? So we're defining factorial, and then we're referring to that definition here in itself, in the definition of itself. We're referring to the function we're defining, okay? And here we're doing the same. So we're defining prefac as a non-recursive function where g is the thing that we're then going to tie together with its own definition. Okay, so we're making g an argument, so that's why the prefac has g as its first argument. And then here, to make it like the original factorial, we'll say, okay, we'll plug in the fact2 that we're defining. So we're, again, tying this recursive knot here. And we're getting the same effect. Okay. So let's reload this. And now, so fact2 of 5 is also, it works. So you might wonder, how does this work? Well, again, this works because it's equivalent to that. As we saw by expanding what prefac means, what it stands for, and then just putting fact2 wherever we had G in the definition of prefac, right? So we have this, and now it says basically fact2 is this, which is the same as the definition of fact. Does this make sense so far? So the question is now, can we do this kind of thing more generally for arbitrary recursive functions? And, that's where we're about to get to. But let's first, play around with this a little more. And let's look at something. So, can we do it without defining fact2 explicitly? So can we do, for example,
using an anonymous function kind of thing?
well, prefac, is not anonymous, but it still takes that argument. Okay. So, for example, what happens if? So, what is the argument type here? Oh, int to int. What other functions from int to int do we have? Well, we have, for example, identity. So what if we apply prefac to identity? What do we get? Let's try that. What do you think we will get? I mean, you can answer it from the code here. If G is identity, what do we get here for this? So let's predict what we get. No more guessing. No more just playing around with it. Let's predict it. So suppose we invoke prefac with G being identity and N being 5. What do we get? You can see it from here. So N is 5, so we go into the else branch. 5 times 4, exactly. So identity applied to 4. So we should get final result of 5 times 4, right? 20. Okay. Let's try that. So like this. Whoops. This. I'm so used to, the Q there. Right. So here it is. So it's the 20. That's right. That's right. Okay. Good. Getting there. Okay. What happens if we apply this to 4? That's right. So what about 3? If we apply it to 3? So I think we're seeing pieces of the chain, right? So now the question is, how many times does this nested invocation of the prefac need to be there? We'll see. So let's say if we put 0 nested invocations of prefac, it's not working, right? Because it's not working because it goes down only by 1, and then it returns right away as if that were the base case, But we also saw this, right? So we saw, so here, what if we tie those together? What if we try this? And now identity. Okay, so what happens now? So we put in prefac identity as G and 5. So we get the 5 here, and here instead of identity, we get prefac identity of 4. So instead of the 4, that gives us the 4 times 3. So we're one step further, right? So here, if we do this, we get 5 times 4 times 3. That's right. Okay, not quite enough. We need one more, right? So we need another prefac here. And then we're already good with the first one, and even if we don't do that, yes?
How come the prefac doesn't always need an N argument? Or if it does, where is it getting that N argument?
Okay, that's a good question. So the prefac is a function that returns a function when you give it only one argument. So if you give it the G, what you get back after that one step, after just giving it the G, you get a function that's still waiting for the N. Okay, so that's so-called currying or partial partial application of the function to only the first argument. Okay, so then so if you give it just a g, okay, what you get back is a function that will still want the n, but has whatever you gave it as the g put in this placeholder. Okay, so then you can give it the n. So if we look at these experiments, right? So here, that's why there are two pairs of parentheses. So here, we're giving it identity, and if we actually write that, okay, so if we say prefab, just identity, like this, it says, well, that's a function, and to treat that as a value, you have to give that underscore. That's a Scala thing. In Haskell, it would say, okay, you got this function. But in Scala, because of this thing between functions and methods and so on, there's this syntax issue here. So once you have this, this should be the function that you get if you apply prefab only partially to the first argument. So we're passing identity as the g. So this should be the function that goes from int to int. So that still wants the n. Okay, so you see that here. And it tells you, yep, it's from int to int, and it's a function. So this I can now take. See how in the REPL they automatically get these consecutive identifiers. So if I put 5 in here, that's when I give it the n. And up there, at the top, I'm just doing these two steps together. Okay? But what I can do is I can say prefab applied to identity, which still wants the n. That is also a possible actual argument for the g. Because g is of type int to int. It takes the int and produces an int. And we saw here, prefab applied to identity is of that matching type. So that's why we can plug this into here as the argument. Okay. So if we did that again, okay. Whoops, that is always a undesirable situation. Okay, so we'll bring it back. We can just load the worksheet. Okay. All right. So what we had is this. So this should give us 5 times, and then because we had one more level, we get the 4 times 3, right? So we got the 60. So what if we do it one more time? Then it should go down to 2. So it should go 5 times 4 times 3 times 2, and then technically to make it match exactly what the definition is, we would need to go back down to 1 and then to 0. But it won't make a difference anymore at that point. See? So here we got it. So technically, we need to multiply it by 1 twice, so we need to put these 2 more levels like this. Okay. Now that's weird.
You put one more.
I put too many, yeah. That's right, so that's kind of weird. Oh, yeah, that's right. Okay.
It never produces 0, does it?
No, the identity, when n is 1, that's right. So that's a good thing that we noticed. What happens if you put too many recursive invocations? That's right. So here we have the right number now. Okay. Okay. So for this argument, if we have the long enough chain of applying prefab to itself, we basically get the same effect as what we have with our recursive definition. But what if we go up to 6, it'll still work, right? But if we go to 7, let's see, we can compare that with the right value. We're missing the 2, you see? So if we go larger again, like for the 7, then this chain is no longer long enough. This chain of basically nesting or recursive invocation depth. All right. So we're a little bit stuck. I mean, we can get the right result for specific argument values by predicting how long or how deeply nested the first argument of the prefix should be to have the right length of that nested chain for the right argument. Does that make sense? So that's what we can achieve, right? So if we put this many, it'll work for, let's say, 3. So we put 3, it'll give us, oh no, that was 1 too many for 3. So, but for 4, it'll give us 24, right, which is 4 factorial. It'll probably also work for 5, yep. But then that won't work for 6, because that should be 720, because again, we're at the point where we're losing the times 2 at the end. Okay. So what we are able to do is, for a given argument, we can figure out how many times we have to apply prefix to itself with the identity as the base case, which doesn't take a g as an argument. The identity works on its own. Prefix needs the g argument, and then it needs the integer. Okay, so that's why the identity plays this role of the base case here. I have another idea. You will love this. This is really good. This one is really good. You will see, because I'm glad I remembered, because this idea of having to figure out how long the chain can be at most is not good. Check it out. Okay. So this really rocks. So, okay. Check this out. Okay. Good. Yeah.
Is this still a recursive function call, right? Or
there is no recursion here.
but we are using the prefix.
We're applying it to itself.
Yeah.
So.
But it turns into an argument.
Yeah, but it's the function prefix is not recursive, but we are. It's just like, if I did, for example, this. If I said, 1 plus 2 and then plus 3, it's kind of like that. So it's no more recursive than this. We're just kind of nesting this application. Okay. Because what we have here is the same as saying, underscore int plus 3, right? And then that applied to 1 plus 2. So it's kind of at that level, right? Where here instead we'll have a more deeply nested expression involving more applications of prefix. Just like here we have the plus and then we have the plus again, and we can have more complex expression having more uses of plus. Okay. But all right, does that make sense? Yeah. So there's no recursion right now. Okay. Now this is the secret that will allow us to make this intellectual leap. Because identity didn't do the job. Why not? What's different between this function? I have to show you what it does. Okay, so if I give it a 1, it produces a 1. What if I give it a 2? What do you think it'll produce? No, the type, okay, wait. The type is int to int. In fact, it's more general. What if I give it a string? What do you think it'll do? It says it's going to produce an int. Where? That's right. And there we go. Okay. So now, check this out. This is the part you love. Okay. Look now. Okay. So prefix. prefix. Identity first. Okay. Okay. Oh, more parentheses. Okay. Oh no. Okay. We need the parentheses here. Fine. Wait, didn't we have 0 for this before? Now I'm confused because before we had. There was a time when we had a 0, right?
Yeah.
Okay, let's try this again. So load.
Try with 1 extra.
Maybe, yeah, but no, it shouldn't bring it back. So okay, well, where did we have the 0? Okay. Well, what if we introduce another prefix here? Okay. Yeah, but anyway, so here's the thing. So if here we plug in the function const1, we all still get the 6 back instead of the 0. Okay. So that's the thing. So here it doesn't matter actually how long the chain is, you know. So if it's longer than expected, you know. Okay. So here it's too short, right? 5 we get 60 instead of 120. But the thing is, so now with the const function, and that is really the key thing. So we can add as many elements to this chain as we want, and the thing will work, you know, as long as there are sufficiently many of them here. Okay, because then at the end, when it gets to the point, let's look at the definition. So where G is identity, the issue is when G is identity at the wrong point, when n is 1, and that is, in a way, that could be corrected very easily here. So if we do it like this, okay, then we wouldn't need the const. So let's just do it like this. Okay, so if n is 1 or less, then we'll go back, because then we only go into the else part if n is 2 or more. Okay, and now we can see if the chain is longer than we need. It'll never make it 0, because the last time it'll go into else is for n equals 2, and then it'll use identity here, and then when n becomes 1, it'll go there. So in this way, it'll always be okay. So let's do that. But the const, you know, otherwise we'll take care of it nicely. Okay. Yep, okay. Very good. So let's reload. Okay. Yep. So now the problem is gone even for identity. So this will always work as long as the chain is long enough. Okay. So with 7, it's not long enough because that should be double that. So here we're losing the 2 again. Okay. So where do we stand? So if the chain is not long enough, we're losing some of the lower factors. Does everybody see that? If the chain is too long, it doesn't matter. So how long to handle any argument does the chain have to be? infinitely, basically. That's right. So that's exactly right. So the next step, what we're about to try, is to write a function that basically has the effect of instead of having a finitely deep nested invocation of prefab, having something that has as many as we pull from it. Okay, so effectively infinitely, but there's not going to be an infinite structure in our program. It's just a structure that can generate on demand an arbitrarily long chain. Do you see the difference here? So we're not pre-computing an infinite structure because that would cause us to run out of memory immediately. That's what you saw earlier when things weren't quite right. It would cause a stack overflow, for example. Okay, but what we need is essentially instead of a finite chain of prefab, and at the end identity, we want something that, as long as we invoke it, it'll generate one more level on demand. And when will that demand end? When n becomes small enough so we no longer go into else. Right? So then we go here and we don't create any more demand on that chain. That's basically what happens. Okay, so this is what we're going to do. So if we can define a function that takes f, where f is, for example, our prefab, okay, and then we have basically a function that goes from whatever the type of f is to that same type. I mean, more clearly, if f is of type a to a, where a might be integer, okay? So if f is if f is of type a to a, then applying y to f gives us something of type a. So what is type a? Well, we want the result of taking f and making it kind of recursive by using y. We want that to be a function. So a needs to be something like int to int. So a needs to represent the function type. So a to a would be something like int to int mapped to int to int. So it's like the type of our prefab. If we type prefab underscore, it'll tell us, and it'll say int to int, arrow, int to int. You see? So our a is int to int, and this is a to a. Does that still make sense? So when you match a arrow a to what we have up there, each a matches int to int. So we take this prefab, we apply the so-called y combinator to it, and the result is just something of type a, which is just an int to int function. So it's a function that takes int and produces an int, just like the factorial. This is the result type that we want. So the function that we plug into the y combinator needs to be something that takes a function and returns a function by basically applying one step. And that's what the prefab does. It performs one of the multiplications in this longer process of computing a factorial as a chain of multiple multiplications. Okay? So the y combinator in Haskell, you can just write it like this and it'll work. Okay? But in a strict language like Scala, so Haskell is a lazy language, so it tries to compute things only when you're trying to actually get the value. So it doesn't pre-compute things. Whereas Scala is a strict language that pre-computes eagerly in most cases by default. So in those languages, you need to have a little variation where you have an explicit argument n here. So you have to write it like this. You have to write the Y Combinator as kind of like our prefac, but a generalization of that. Okay? So the way it works now is, so this F, again, is like our prefac example. And if we write it more conceptually, you know, as opposed to as a method, if we write it as a function with argument, arrow, and then body, in this case, the body being another function, and then another arrow, and then the actual body. So this is what our prefac looks like. And then here the body is the if-else thing, and the G occurs in the else, right? So when we wrap the Y Combinator around F, such as the prefac, what it does is it replaces, remember the F takes a G. And so in other words, this is the G that the F gets. And this means, oh, we're getting the whole chain again. So meaning Y applied to F represents an arbitrarily long chain of F applied to itself. And when we apply that, we define that chain as F with the argument of F being provided with that whole chain. So that's how you get the arbitrarily long chain. So as long as you want to call the G, you're getting Y of F. And then if you call it G again, you get another Y of F. So it's like having an infinite supply of prefac applied to itself. And why doesn't this become infinite? In terms of, why and how does this computation end at some point? Yes?
Well, because at some point, prefac is not going to call for a G, it's going to just go to 1. Right?
That's exactly right. When the n is such that we just go into the then part of the if state of the if expression. That's exactly right. That's how it works. So it's okay to have that infinite supply of the chain, but as long as the function body is written in such a way that it's at some point it branches away from continuing to call into that chain, it's not going to try to use up the chain, even though it could go very deeply into that chain as long as it wants. Yes?
So at a lower level, this actually has the same effect as recursion, right? You have everything goes on the stack, and then
this is exactly the same, right? We're just making we're just becoming aware of recursion. We're just kind of making the recursion explicit. So this is at some abstract level similar of other things we've done, where we're separating different concerns. So for example, we have separated in some other examples concerns of structuring our data and concerns of behavior that we get for that data, right? Like we have the shapes that we just, we can arrange them, and so we have some structure. And then we have behavior such as bounding box or size or those kinds of things. So we have a separation here. Now, this idea of separation of the structure concern and the behavior concern, the idea here was separation of concerns. And if we apply that idea to something like this factorial at the top, we say, well, there's the concern of, branching depending on the n, so kind of the behavior part, what to do for a particular n, and then there's the other concern of kind of tying this recursive knot. And that latter part is common for all these similar recursive functions. That's why we were exploring the possibility of abstracting that out and having that only once, and then being able to write all of our functions non-recursively and then just saying, well, if I apply the y combinator, then it becomes a recursive. It behaves like a recursive function. So, in that sense, we try to separate those to see how far we can get with that, and we are, as you're about to see, we are able to define this y combinator like this. So in other words, now f can be non-recursive like the prefac, and if we invoke y of f, if we apply y of f to n, then we get the recursive behavior just through applying the y. So that is how we explicitly introduce recursion. So in other words, as long as you have this kind of building block, like the y, you don't need the language to have recursion as a kind of built-in language mechanism. So if you can have that y, and in fact, there are. So this is something we'll explore in Project 3. But there are languages in which you can, languages that have no recursion explicitly, but that are powerful enough so you can define the y from scratch. We can't do that here in these languages. But there's the untyped lambda calculus is powerful enough that you can start basically with nothing and create the y combinator from scratch. It's amazing. Here, it's coming up right here, so it looks a little weird because all the typing is explicit. Here it is, okay. So this is the Scala definition of the thing at the top. Okay, I think you need me to move this up just a little bit. Okay. Can everybody see this above my screen now? Okay. All right. So again, this is just the typing. So above we said A to A to A, but because we said, well, the A stands for a function from something to the same thing. The A is now what is in our situation above in our concrete example, the int. Okay. So let's say, so A is just the argument type of the function that we ultimately get, the recursive function. So what y takes is a function that takes a function from A to A and produces another function from A to A. So it takes such a function, and the prefac is such a function for which A is int. But prefac takes the G, so this plays the role of the G, and it produces the result of prefac, which is the branching for n, and making the other call for larger n. Okay? So this plays the role of the argument of prefac G, and this plays the role of the result of prefac. And the result of applying y to prefac is of this type, again, where A is int. So that's just the same type as factorial, just a function from int to int. And we're just generalizing it to arbitrary A because we can. So it'll work for arbitrary A's, your list or whatever you want. And here's the definition. So it's just given f of that relatively complicated type and given n of type A, that corresponds to n. This corresponds to the whole thing here, okay, like prefac. So given f and n, we want to give y of f to f in that first argument. So this provides the arbitrarily long chain of f applied to itself to f, if it wants it, if it uses it, and then we're applying the whole thing to the final argument n. So if we have the prefac, if f is our prefac, this says basically y of, so it will say prefac y of prefac of n. Okay? And we'll see that here. All right? So we can then now define the factorial. Remember, prefac is non-recursive. So we now define just by using y. There is no recursion here. This is just applying y to a function. The recursion is now completely hidden, in only one place, which is y. So y handles our recursion concern. So it's completely separate from everything else we can do now. So prefac is non-recursive. We'll say, let's convert it. So prefac has this type for a equals int. Let's convert prefac into a recursive, or into just a function, which happens to be recursive, by applying y, and it'll work. So the mechanism that's at work is here. So this is actually a mathematical proof, how it works for n equals 3. So y applied to prefac applied to 3. So we just apply the definition of y, which is f of y of f. So we replace y of f by f of y of f, right? And now we apply that to 3, because we cannot apply the thing that starts with the y easily, because we don't grasp that, but when we have the actual prefac, we know that has a body. We can plug the n into the body. So here n is greater. So we go in here, we replace 3 for n in the body, and this is what we get, substitution. And then because of the way if works, we get the else part. And we continue. So now, again, we have y of prefac. We do that again. So we take one more item from the chain. And we get that same thing again. We do the same substitution. And then here it says again, y of prefac. We've got to do that again. So that's prefac of y of prefac of 1. Now we put the 1 into the definition of prefac. And now, with the way we altered it, now this goes into the then part and returns 1. So we no longer need to pull more. We no longer need to unravel, or pull out that chain, so to speak, as soon as we reached our base case. But as long as we haven't reached the base case, the y of prefac expands arbitrarily many times to prefac of y of prefac. That's how we introduce the recursion into it. Does that make sense? By putting this combinator in there. So you can actually see this here. So anyway, okay, so if we have again, so if we start with identity, we just get one step, because it goes into else and multiplies with, so G is identity, so that's that applied to n minus 1 is 4, and it just multiplies the 5 times the 4, and identity is not, doesn't invoke any more G or anything, so it comes straight back with that. And then we have these various chain examples here, right, where it actually did the job, and then here the chain wasn't long enough, right, for the 8. Factorial of 8 is actually greater than that, right? See where it loses the lower factors. So now, by plugging in y of prefac, we'll get those back, okay? And then by the way y is defined, that's the same as just saying y of prefac. Okay. Yes?
Is there a reason that something like a factorial function ought to not know about the recursion? Like, because to me that function doesn't make sense unless you know either about the iteration or the recursion. Like,
right. Okay. So in terms of, let's say, practical software engineering, let's say, you start with a behavior you want to implement. So that behavior is defined recursively, right? So mathematically, factorial is defined recursively. So the most natural way to implement that is to say, okay, well, I just write a recursive function. That's right. So you have a point. But what we're trying to explore here, is a little bit of kind of the deeper structures that are underneath this. So how does the recursion actually? How is it manifest? Let's say if I have two different recursive functions, what do they have in common? And so you can then separate out the idea that there's this kind of the idea that there's kind of a knot being tied between the thing that we're defining and the fact that the thing calls itself recursively. So the reason that you think that this is normal is because you're used to working with languages that support this directly. Okay, but we're trying to because we're then trying to make an analogy from this to recursive types, which we're used to, and then having non-recursive types where we do this kind of knot tying, like with the Y combinator at the type level. And there's real value to this in the following sense. Okay, here we're not really seeing it because we're saying, well, this Y combinator is just a really simple definition, and it's just as simple to write the function directly recursively. Okay, and it's probably clearer to understand for anybody who's used to expressing behaviors recursively. But the analogy with something that we already know that I can offer at this point is if we have something like adding the items in a list and finding the maximum of the items in a list. Okay. What do they have in common? You could write each of them separately as a recursive function over the list, right? Like the style of, let's see, like the way we did with the reverse and those things, right? So I could write a sum. I could write a sum with a recursion like this, and a max as well. And they would be very similar, okay? But there would be a slight difference. So the question is, what's different and what's the same? And it turns out that what's the same is what? Something that we started to use in our coding style. Let's say if, and in fact here, this example actually illustrates this. So the sum would be, okay, case nil, we would get 0. Case non-nil, we would get h plus sum of t. Right? So we invoke it recursively. So it's just like reverse. So what's the commonality between reverse and what's really separate? And here, the only thing that's separate is whatever you do in this function that you apply in each step. And the rest is the commonality, the recursion pattern, is articulated by the fold left in a very reusable way. Okay? So in the case of the fold left, I think it's very easy to see that when you do these kinds of things, when you write one fold left, and you write many different functions as just ways, as applications of fold left, you have a software engineering benefit in the sense that you're not repeating every time the code for the same or similar recursion pattern. So that's the point I'm trying to make. It's less obvious with the Y combinator, of course, but it's still valuable to understand that we can pull out not only a recursion pattern over a list, but we can pull out recursion in general and say, well, we don't need the ability, if we have the Y Combinator as just some building block, we don't need the ability to express a recursive function in the language like the factorial at the top. Okay? And, you know, of course, I'm cheating by using recursion to define the Y Combinator here. You know, so I'm just saying, well, the Y Combinator is going to be the only place where we're using that capability. Fair enough. But that's where the other consideration comes in, that when you go to other similar languages, there are some that are powerful enough that you don't need to build recursion into the language, and you can write the Y Combinator non-recursively from scratch. That's very powerful, right? But I agree, you know, the software engineering benefit, when you just look at, let's say, writing this, okay, as opposed to the factorial at the top, you know, there isn't really a software engineering benefit here. It's really more of the conceptual understanding that if we want to, we can pull recursion out completely. We don't need to write any more recursive functions. We just need to write them in such a way that there's an argument, an explicit argument, where it can then tie a knot. Like basically feed this G, tie it back into here, right? Form that loop. You know, just like here it's basically by name, and here it's by applying the Y Combinator, so it puts that unlimited chain back into here. So that, you know, that's basically what we saw here in this example. Good questions. Any other questions, comments? So let's do this. So let me get you started on the expressions example so that you can start making some meaningful progress on project 2B. You know, at least you can get started. It'll make sense. You can kind of match things to the expressions example. So that stuff is in the Scala mu examples. Now, where is that? So I have to open that. Open. Scala mu. Okay. So what is Scala mu? Well, it just popped up. You know, I basically converted it was called algebraic explorations or whatever, so I just converted it into a little more of a proper project with a little bit of a library, and then, you know, here's kind of the quick start. That's what we're going to look at now in more detail. So there's the library part, and then there are the examples, which are the worksheets. Okay. And this is how you can use it as a library, or, you know, you could just clone, if it's easier for you than installing this plugin. You know, you can clone this and then kind of put whatever you can reuse from project 2A, you know, the shape stuff. You can just retrofit that into this project structure. Then you don't need to deal with the bin tray plugin that pulls the library in binary form from a repository. Okay. Yeah, bin tray is a thing where you can publish artifacts, you know, which is very easy to get access to, very uncomplicated or non-complicated. So, okay. Let's look at some of these examples. So the order in which you'll want to look at them is you'll want to start with expressions. That's kind of the most accessible because it's like shapes, you know, like those kinds of things. And I'm wondering now, is there an expressions example? Yes, an ordinary recursive one. So what you'll want to do is you will want to look at expressions-scala. So basically what your project 2A is to expressions-scala, your project 2B should be to the scala mu expressions example. That's the analogy. All right, so let's go in here. So here we have these expressions like, these nodes in an expression tree structure. So it's just like the shapes, but it represents arithmetic expressions. See how this is the ordinary recursive type following that usual scala pattern with the sealed trait, just like shapes, right? What's the key difference between this and shape? Well, there are several kinds of things that are like group, like the composite, and there's a fixed number of children. But other than that, it's just like shape. And there are some methods that are even the same, some behaviors. So, there's size, there's depth. Remember, this looks very familiar, right? Except you had to use a max over all the children, an arbitrary number of children, and here we just use the max of 2 arguments recursively, right? Other than that, it's just the same, size, same stuff. There aren't any of these, well, unary minus is kind of a decorator, right? All right. But the nice thing is, and this will be the underpinnings for our project 3, there's an expression evaluator. So, for example, if you're evaluating times, you evaluate the left sub-expression, you evaluate the right sub-expression, you get the 2 integers, and then you multiply them as integers. It's very straightforward. Your typical 271 expression evaluator. So that's why we're not looking at this as a project at this level, but we're using, because it's so easy to understand what this does, we're using this kind of at this level, or the shapes are also easy to understand. We're using these things as examples for pulling out the recursion pattern of the type. Again, we're going to so what we did before, until now, and what the Y Combinator was kind of the culmination of, was pulling out recursive behavior. Now we're going to focus on pulling out the recursion pattern in structure. Okay, so here there's the recursion pattern, right? Plus is an expr, and plus has the 2 sub-exprs. So that, the essence of the composite pattern, where you have the is a and the has a, 0 or more, or exactly 2 or whatever. Right? So jump in if something I'm saying is not making sense. But we're intimately familiar with these kinds of things. This is so close to object-oriented style with the subclasses that it's highly familiar. It's just a lot shorter than having to have a one-page class for each of these things. Okay. So the expressions is taking this and turning it into something where we're pulling out the recursion and separating it just like we separated the recursion from the factorial using the Y Combinator. But here we're doing basically the same thing structurally. Okay. So really what project 2B is redo this but with shapes, basically. So use the technique of going from this expression example to that, going from that one to this one. So that same transformation you need to apply to your project 2A. And then what you have for project 2B should look kind of like this. So what do we see here? Now there's this algebra terminology, which is really for our common amusement. It might look intimidating, but it's really no big deal. Trust me on this. So don't get intimidated by this. People can very easy even for a regular guy like me to spend a weekend and read up on this stuff and then just put it here in the comments. So, if I can do this, so can you. So when you see endo-functor in the context of programming, it really just means a unary type constructor, something like list or option that wants an element type. Does that make sense? So, but strictly speaking, so it's something that wants an element type plus a operation that behaves in certain good ways. And for a functor, the operation you want to think of whenever you hear functor is map. Okay? So for option, we have map. What is the result if you map a function f to none? We saw that earlier, I think. You have none, and you map the identity function, for example, or +2. You map that to none. What do you get?
None.
You still get none. That's right. What if I have sum 7 and I say map +2 to that option? I get sum 9 exactly. So that's the map, the idea of a map, and you saw it for list. Where I can map a function f to the list, and it just means you apply f to each item in the list. So those are all functors. You're already using functors. The only difference here is that this is a nonlinear functor that kind of corresponds to the expr, this recursive expr type. See, so option, yes, is non-recursive, but list is recursive, and there's a relationship between option and list that we can explore. In fact, option leads to list, and list leads to tree. So these are, there's this hierarchy that we can explore once we're more comfortable, kind of more at this working level. Starting with this simpler example. Anyway, so option is an example of an endo-functor, and what makes it an endo-functor is that it takes a type as an argument, the item type, and when you say option int, it's still a type. So endo means it stays within certain kinds of things. So it takes a type, and when you apply it to a type, the result is still a type. So if the result were a number, it wouldn't be an endo-functor because it would go from types to numbers. We don't have such things even. But here, option, list, and this expr f, they go from type A. So you stick in type A, for example, int, and the result is the type expr f int. Just like when you take option, you stick in int, you get option of int, and that's still a type. So you're staying within. The endo means within this, it's called a category of types, okay? So that's why you're seeing that here. So the endo-functor is a type constructor that you apply to a Scala type, and out comes another Scala type of, namely the type constructor applied to the item type. Okay. And A is the argument type, and let's see, the structure, the rest of the structure is the same. What is the only one difference? So before, we didn't have an item type here, right? And here we had recursive references to that common supertype. Does that make sense? So we can look at that here. Okay. Oops, let me get rid of this. Okay. So here, left is of type expr, and that's this common supertype. And here, left is of type A, and that's now a type argument. So I think you might guess that it's going to be a little bit like the prefac. This is like the prefac. And then we'll have a thing that's like the Y combinator. the question is, what do we gain here? But so if you bear with me, you will see that there are real software engineering benefits in terms of having common behaviors, like fold, similar things to fold or other recursion patterns that we need to write only once, really one version of this, and it'll work for option, list, tree, anything else you build within this framework, including this stuff. So that is the endpoint, kind of. Okay. Anyway, so for this to become a proper functor, so you can see how you could convert your shapes hierarchy to this, right? You have to introduce a type parameter, and wherever you see shape recursively, you just replace it with that type parameter. So you introduce the A, and wherever you see group, for example, shape star, you put A star instead. Right? Mechanically, that's how it works. So in other words, you're kind of untying the recursive knot, and the A is basically the slot where you can tie the knot. Okay. And it'll take time for this to make sense to the extent that you feel like you're fully understanding this. But it's the same idea really as the Y Combinator, where the recursion really means, well, you have an unbounded supply, of like an unbounded chain where you can pull things. And when you have that, you consider that to be the recursive version of what you had. Okay. All right, so we have this type constructor. So this corresponds to list or org chart. Very similar. All of these things are similar. Org chart is a little more complicated, and so is list, because there's also a generic item type. This A is not an item type. That we have to be very clear on. Shapes and expressions don't have an item type like list or option. Does that make sense? The only things you can have in these expressions are ints. That's why when you look at constant, that is really not parametric. Does that make sense? So that you can only create with an int value. Okay, so that's fine. So same with shapes, right? A rectangle is not generic, and it will not become generic by introducing the A argument here. That is the one thing I wanted to point out. Okay. So you'll get something like shapes F, or shape F, singular, shape F parameterized by A, and then all of the actual case classes will be parametric in A, and they will refer the ones that are not leaves. So obviously some of them are leaves, so those correspond to constant, but the ones that are not leaves will have an A instead of a recursive use of shape. Okay. So how does this become an actual functor? Right now it's just a type constructor, basically. How does it become a functor? What does it need for us to be able to say this is an actual functor? Okay. So this is what I'm telling you now. It needs a map. Okay. So you basically need to, this is Scala Z stuff here, but you can just follow this same pattern. You need something like a shape functor, and you need to define map for, it can follow this exact same pattern. And the way it works is wherever you have something of type A, you need to apply F. So in other words, you're kind of pushing the function application into the structure. Just like, when you have sum 7 and you apply plus 2, you're pushing the plus 2 into the structure and you get the sum 9. So same thing here, so the constant is where you don't, because that's an int. And the f, you don't know whether a is int in a particular situation. It has nothing to do with it. So in other words, these leaves are invariant under map. Okay. Just like nil, nil or none, those things like empty list or none, they don't change when you apply map something. They stay the same. So it's the same here. So constant is like that. But anything where there is an occurrence of an A, those values, you need to map them to something similar of type B. So what changes and what stays the same? Let's say you have some kind of instance, you have a plus, and you apply map to it. What stays the same and what changes? Does that change from plus to something else when you apply map? No. And that's really the beauty. So the map function, or map method, it's what's called a homomorphism, meaning it's structure preserving. So if you have, let's say this kind of tree, 1, 2, and 3, then you can map it to something like, string 1, string 2, and string 3. All right. You see how the map did its job. So the f goes from number to the corresponding string, and you just push that into the structure and apply it to each element, and you get that. So it's just like that. All of the maps are like that. This is how functors work. And there's some properties like the identity law, or then this. Let's see. Let me remember this other one. So there's there's a composition law. Okay. Right. So this is also very easy. So if now you map again, and the function is duplicating, concatenating every string with itself, you get 1, 1, you get 2, 2, and you get 3, 3. But you still have that same structure, 1 root and 2 leaves. And so map F, and here map G, but you could go also here by mathematically composing F and G first, and then going in one step. That is one of the functor laws. The other one has to do just with identity, that if you take the identity, that it doesn't have an effect. Okay. So, functor law of composition. But normally most map implementations that you write reasonably on these straightforward structures, they will do this automatically. So this one, it does it. Okay. So now the question is, there are two questions. One is, how do I basically use this, which doesn't have a not tied, okay? And what do I gain from all of this? So basically, the first question is, how do I take this and get that? And that's where Scala mu comes in. So that's the equivalent of the Y Combinator is this. Okay, the mu here. So there's a challenge, of course, figuring out how to type that. On the Mac, it's easy. You just say option M. Okay, but you don't have to type that because the way the library is defined, and you can maybe guess how many lines of code are actually in this library, and you'll probably guess wrong. I'll show you here. Make your guess now before I expose it. Okay. Well, it's really very little code, right? So there's mostly comments, and so you can write mu like this. So it's the same as that. All right. So the only piece of new code is really the only piece of new code is this. So there's really only one proper line, but then there are a few things where it forwards methods to other methods. Anyway, we won't look at the internals yet. We'll look at this at some point. Anyway, so this mu is like the Y Combinator, and if we say mu x per f, it's like getting this back, because now it kind of ties the A back into x per. Okay. So what you're seeing is that this idea is possible at the type level. So that's this part. And then here, these are just convenience methods because there's a price to pay for using the mu. The price is you cannot just say constant C and get an x per. With constant C, you're getting an x per f. But you want an x per, so you also need to apply the in. With the in, you're getting you're wrapping the x per f into an x per. So that's why it's convenient, before you start creating your instances, to have these little factory methods. So you'll have similar ones for the shapes, and then you can write these things just like that. Okay? So, same for the shapes. Your fixtures will largely carry over. You could even, name them in such a way. That would be a good test. If you actually name the factory methods in such a way that they're consistent exactly with your existing fixtures, and maybe name these things a little differently. Maybe with an underscore at the end. That might not be so good. But something lowercase or a different case of the factory methods. But I would make the factory methods from which you're building the fixtures consisting with your existing shape fixtures, and you can then immediately see if you did it right because your existing shape fixtures will work. Okay. So far, so good. But now the benefit. Okay. So basically, if we look at size now, so again, this looks fancy, but all this is, if you look at the definition of algebra, if you look at the definition here, it's just a function from the functor to the element type of the functor. And it plays this role of an algebra. But basically, this just means, how do you get an int out of an x per f of int? And that captures the step I have to perform as I'm computing the size. So if I have a constant, well, I know it's a 1. But if I have a unary minus that has a sub-expression of size r, then my own size is 1 plus r. Or if I have a plus that has sub-expressions of sizes L and R, the resulting size is 1 plus L plus R. Okay? So I can express the computational part in this way. And here, L and R are not expers, they're ints. That is the difference. So the assumption is, what if these are already ints? And this should remind you of something a little bit. In which operation that we're already familiar with do we have a way to describe what happens at each step, where one of the argument is the result we already have up to that point? Yep. That's exactly right. This is very, very similar. So the fold left is kind of a special case of what we're doing here. It's exactly right. So with a fold left, we have two branches, but the branches are not explicit because the fold left takes two separate arguments. This is like a fold left with 7 arguments, but that's why you don't write it like that. You write it as a branching. The fold left has an argument for empty list and an argument for non-empty list. And for non-empty list, you get the item that you're currently looking at, and you get the result you've computed for the list, the portion of the list you've seen up to now. And these things correspond to the subtree you've seen here and the subtree you've seen there. So it's basically the same idea. And now, the general fold left is this kata, and it's called kata for katamorphism, meaning, and this is Loyola, so humanities, classics are important here. So in Greek, katamorphism means when it's related to catastrophe, when you're taking a structure and you're reducing it to a result. Okay? So, and that's what the fold does, right? So, for example, sum as fold, you take this big list, you say sum, and you just get this little number as a result. Same thing here. Evaluating this arithmetic expression, you just get one result. So, same thing. So, think about the kata as the fold, and the evaluate, these algebras, as the thing you have to do for each node, which describes basically the branching you have to do for each node. And now you can see also the max looks very familiar. The depth, right? So depth, you just use max. So these things should look just like what you did earlier, except you're not invoking explicitly the behavior recursively on the children. That connection is made in this general way by the katamorphism, just like the fold left allows you to focus only on what needs to be done as you look at one item, and it takes care of putting everything together and traversing the structure. So the katamorphism, if I expressed list in this same framework, I could use this exact same katamorphism code. So, this is kind of the preview. That's basically your software engineering benefit. I need to write only one katamorphism ever for any of these kinds of structures, okay? And just the one thing, and then we'll need to transition to the presentations. Guess which functor allows us to build the list? Because we have, you can kind of guess, I guess. So with list, you have, when you're looking at each item, as you're processing a list, what are the two choices? Either you're at the end, or there is an item. So what simple functor does that correspond to? Either you have the end of the list, or you're looking at an item. That's right. Exactly. So when you build this kind of thing over option, you get list. And then when you build this over list, you have a node and you can have 0 or more children. So when you take list and build this kind of stuff on top of list, you get trees. So, that's kind of the beauty, the deeper structure here. How these things ultimately become just building blocks. Anyway, I'm hoping that I got you started enough so that you can make meaningful progress on the actual project. So try to focus on developing what I call, and this is kind of my learning style, it's an inductive learning style, try to develop a working intuition, and then you will gradually understand the more formal foundations underneath these things. So don't expect to understand necessarily all this terminology or make sense of it. I wouldn't even worry about it. I think you can, when you look at this X per F example next to the conventional recursive type X per example here, and then you look at your shape example, then I think something like this for shapes will pop up for you, right? That's basically where I'm hoping we can get. But you will get guidance from me, and we'll discuss things as everybody makes progress on this and works on it. But I think you believe me. I hope that you need to do this with a partner. So if you're not part of the group yet, form one right now. So let's transition to the presentations, and we are going to have a presentation on Haskell, right? So you can just come down as soon as you're ready, and then we're going to have a presentation on F#, right? So that's great.